Igneous rocks, if you didn't already know, are the rocks that form from molten material, often associated with volcanic activity. For many, this conjures up images of volcanic eruptions with lava flows bubbling and oozing across the landscape, as seen on the island of Hawaii. As the lava cools and hardens, a new igneous rock will have been born. Of course, not all volcanoes are alike. Some are up violently, such as the famous 1980 eruption of Mount St. Helens in Washington state. Here, the molten material has a different chemistry and a lot of dissolved gases, which make for explosive eruptions that form different igneous rocks. These types of igneous rocks cool and form quickly at the surface during an eruption, but other igneous rocks form slowly, never erupting at the surface, but cooling over long periods of geologic time, deep within the Earth's crust. When we're talking about molten material that has erupted at the surface, we call it lava. As this lava that has been extruded to the surface rapidly cools, it will form an extrusive igneous rock, also known as volcanic rock. Because these rocks cool quickly, the minerals that crystallize do not have sufficient time to grow into large, visible crystals. When we're talking about molten material that remains beneath the surface and has not erupted, we call it magma. If the magma rising through and intruding the crust never erupts but cools slowly beneath the surface, it will form an intrusive igneous rock, also known as plutonic rock. Because these rocks cool slowly, the minerals that crystallize have plenty of time to grow into large, visible crystals. So, when we identify an igneous rock, one of the interpretations that we can make is whether it formed at or beneath the surface. And depending on the mineral composition of the igneous rock, we can also make some interpretations as to the possible geologic setting where the rock had formed. In broad geologic terms, we can interpret the origin of most igneous rocks to have occurred along one of two types of active tectonic settings, convergent or divergent plate boundaries. Let's take a look at divergent plate boundaries first. In places where the crust begins to rift apart, such as what happened during the breakup of the last known supercontinent Pangaea, molten material from the mantle rises and erupts at the surface, pushing the plates apart. Because the mantle is mafic to ultramafic in its chemical composition, the cooling of magma and lava associated with divergent plate boundaries produces dark-colored igneous rocks composed of minerals such as olivine, pyroxene, calcium-rich plagioclase, and amphibole. As rifting continues, entire ocean basins may open up as continents move apart and new mafic ocean crust is formed. Of course, elsewhere on the planet, instead of tectonic plates rifting apart, they are converging on each other. There are three basic scenarios associated with these types of boundaries: continental crust colliding with continental crust, ocean crust colliding with ocean crust, or ocean crust colliding with continental crust. Since continental crust is felsic in composition and has a lower density than the mafic ocean crust, in the scenario involving the convergence of ocean crust with continental crust, the ocean crust will get pushed down and subducted beneath the more buoyant continental crust. As the ocean plate descends into the mantle, partial melting will occur, producing magma that will begin to rise and assimilate continental crust into its composition. In addition, as the magma rises and begins to cool, mafic minerals will be the first to crystallize and settle out of the magma in a process called fractional differentiation. This further changes the composition of the magma such that it becomes more intermediate to felsic over time. If the rising and slowly cooling magma never reaches the surface, it may form large bodies or plutons of igneous rock such as granite, which contains easily visible minerals. If the magma continues to rise, it will form a series of volcanoes that erupt explosively at the surface, rapidly cooling any lava into igneous rocks containing minerals that are too fine to see without the aid of a microscope. This process is happening today along the west coast of North America, forming the volcanoes of the Cascade Mountain Range like Mount St. Helens, Mount Rainier, and Mount Hood, or along the west coast of South America, forming the Andes Mountain Range, which contains numerous active volcanoes. A similar situation occurs when two ocean plates converge, forcing one plate to be subducted beneath the other, producing partial melting, rising magma, and a chain of volcanoes at the surface known as a volcanic island arc. Examples of modern-day volcanic arcs include the Aleutian Islands of Alaska or the islands of Japan. As for the third scenario, when two continents collide, the buoyancy of the felsic crust prevents either plate from being subducted and instead forces both plates upwards. The Himalayan mountains are a product of such a collision as the Indian plate pushes into the Eurasian plate. These types of collisions generate faults, earthquakes, and intense metamorphism, but lack the kind of volcanic activity associated with subduction. Keep in mind, this is a quick and simplified description of tectonic plate boundaries, and there are lots of other variables and scenarios, such as volcanic hotspots, that will affect the composition and crystalline texture of the igneous rocks that form. However, it does provide a general framework upon which we can make some initial interpretations of the igneous rocks that we identify. There are two keys to the identification and interpretation of most igneous rocks: composition and texture. Starting with the composition, it is simply a matter of observing the rock and assessing its overall color. If it is light in color, it is likely composed primarily of light-colored felsic minerals such as quartz, plagioclase and potassium feldspar, and muscovite. If, on the other hand, the rock is dark in color, it is likely composed primarily of dark-colored mafic minerals such as biotite, amphiboles, pyroxenes, and olivine. As an example, imagine each of these three cats represents an igneous rock. The cat on the left is primarily dark-colored, so that cat must be mafic in composition. The cat on the right is primarily light-colored, so that cat must be felsic. The cat in between has a relatively even mix of light and dark colors, so we'll interpret that cat to have an intermediate composition. There is also an ultramafic category, so if our cat was dark in green in color, there's a good chance that it would be ultramafic in composition. So, if we were out in the field identifying and interpreting an igneous rock for the very first time, even if we have no idea what the actual mineral content is that composes the rock, the color alone allows us to estimate the types and amount of basic rock-forming minerals that we would expect to find. We can then follow this observation up with what we know about the composition of igneous rocks at divergent and convergent plate boundaries to make some preliminary interpretations about the geologic setting where the rock formed. Other rocks nearby or within the region may provide additional clues or evidence to support or refute those initial interpretations, and we would certainly bring samples back into the lab for detailed and thorough analysis. For our purposes, though, felsic and intermediate igneous rocks are likely associated with convergent plate boundary settings, and mafic to ultramafic igneous rocks are likely associated with divergent plate boundaries. The second interpretive observation that we need to make involves the texture of the rock, which will determine whether the rock cooled intrusively deep beneath the surface or extrusively at or near the surface. Let me clarify that texture in this context has nothing to do with the way the rock feels in or on your hand, such as it feels like it has a rough or smooth texture, but rather what is visible or not visible to the naked eye. Phaneritic or coarse-grained igneous rocks are those that have easily visible mineral crystals that you can see without a hand lens or a microscope. If the minerals are all relatively large, around 1 centimeter or larger in size, we call this a pegmatitic texture. Both textures are indicative of intrusive igneous rocks that have cooled slowly beneath the surface. Aphanitic or fine-grained igneous rocks are those whose mineral crystals are too fine to see without the help of a hand lens or microscope. This is a texture indicative of extrusive igneous rocks that have cooled rapidly at the surface. Some igneous rocks have what is known as a porphyritic texture, meaning they have large visible mineral crystals floating in a matrix of non-visible mineral crystals. This is a texture indicative of igneous rocks that have undergone 2 stages of cooling. The rock must have been intrusive, cooling slowly beneath the surface, where it began to cool and grow large visible minerals before it was extruded to the surface during an eruption, and the remaining molten material rapidly cooled around it to produce a fine-grained matrix of non-visible minerals. There are 3 other igneous rock textures that you should know and be able to interpret: glassy, vesicular, and pyroclastic. A glassy texture is exactly what it sounds like, which is to say that the rock has the look or appearance of glass. If broken, it fractures randomly and may exhibit conchoidal fracture. This texture is associated with a particular type of extrusive igneous rock that is characterized by extremely rapid cooling, such as would occur during an underwater eruption or when a stream of lava flows into the ocean. Vesicular textures are produced by the release and escape of dissolved gases in lava during an eruption. As the lava cools, the gases become trapped and are preserved. We call these preserved gas bubbles vesicles, but depending on the chemistry and type of eruption, igneous rocks with vesicular textures may appear frothy and meringue-like, or as more solid pieces of rock with preserved bubbles scattered randomly throughout. Pyroclastic textures are produced from the accumulation and deposition of volcanic debris from violent and explosive eruptions. The term pyroclastic derives from the Greek pyro, meaning fire, and clastic, meaning broken. During an eruption, volcanic debris, or clasts, are ejected into the atmosphere. Blobs or drops of lava which partially cool in the atmosphere return hot and simmering to the ground with pre-existing volcanic rocks and hot volcanic ash. This accumulation of volcanic clasts and ash become welded together due to the heat and compaction to form potentially large deposits of pyroclastic volcanic rock. Now, let's take a closer look and compare and contrast all of these different textures and review how we interpret them. Here are two rocks with an aphanitic and phaneritic texture. Comparing the two, the minerals are clearly visible in the coarse-grained sample on the right and not visible in the fine-grained sample on the left. If we mount a thin, transparent slice of these rocks onto a glass slide called a thin section and view them through a petrographic microscope, we can view the individual minerals and identify them. Notice the difference in crystal size between both samples in thin section. This size difference allows us to interpret whether the igneous rock cooled extrusively at or near the surface, or whether it cooled intrusively beneath the surface. Igneous rocks that experience both intrusive and extrusive cooling will have a porphyritic texture. Rocks that have this texture are somewhat analogous to a chocolate chip cookie if you think of the chocolate chips as the large visible minerals and the cookie dough as the fine-grained crystalline matrix. Pegmatitic textures are the result of magmas that remain intrusive and meet certain geochemical conditions that allow for the growth of very large mineral crystals. Most pegmatites that you are likely to encounter are felsic in composition, but mafic varieties do exist. Vesicular textures form due to the depressurization and degassing of lava at the surface during a volcanic eruption. This is analogous to shaking up a can of soda and popping the top, which releases the pressure, allowing the dissolved carbon dioxide gas to explode from the can. The difference, of course, is that the lava cools down and solidifies into fresh igneous rock, trapping and preserving the remaining gases as vesicles. Although there is some variation amongst vesicular textures due to factors such as the chemical composition of the lava, the type of eruption, the volume of dissolved gases, and cooling rates, the part of the story that remains the same is that these are textures that are only formed in extrusive igneous rocks. As mentioned earlier, igneous rocks with glassy textures are usually the result of rapid cooling or quenching, as would occur during an underwater eruption that brings lava into direct contact with water. This sudden contrast in temperature cools the molten material so quickly that the atoms do not have an opportunity to bond and crystallize into an orderly mineral structure, but rather become frozen in place as an unorderly arrangement of atoms. Igneous rocks with pyroclastic textures are indicative of explosive and violent eruptions, so they are by definition extrusive. These types of igneous rocks may be characterized by angular clasts or fragments of volcanic material in an ashy matrix, or it may be composed entirely of fine volcanic ash. So it is the combination of an igneous rock's composition and its texture that allows us to classify the rock by name and make an interpretation of the likely geologic setting in which it formed. Let's run down the list of the common igneous rock types. Igneous rocks that have a felsic composition and phaneritic texture are classified as granite. These rocks may have a lot of color variability depending on the assemblage of minerals, but they will all be mostly light in color and easily visible with the naked eye. The felsic composition is typical of continental crust that forms along convergent plate boundaries, and the coarse-grained texture tells us this rock cooled intrusively beneath the surface. Igneous rocks that have a felsic composition but aphanitic textures are classified as rhyolite. These rocks will be light in color, such as white or pink, and more homogeneous in appearance than granite because the assemblage of minerals are too fine to see with the naked eye. The felsic composition is typical of continental crust that forms along convergent plate boundaries, and the fine-grained texture tells us this rock cooled extrusively at or near the surface. Igneous rocks that have a mafic composition and phaneritic texture are classified as gabbro. These rocks will be dark in color due to the assemblage of mafic mineral crystals visible with the naked eye. The mafic composition is typical of, but not limited to, ocean crust that forms along divergent plate boundaries, and the coarse-grained texture tells us this rock cooled intrusively beneath the surface. Igneous rocks that have mafic compositions but aphanitic textures are classified as basalt. These rocks will be dark in color, such as dark gray or black, and again, more homogeneous in appearance because the assemblage of minerals is too fine to see with the naked eye. The mafic composition is typical of, but not limited to, ocean crust that forms along divergent plate boundaries, and the fine-grained texture tells us this rock cooled extrusively at or near the surface. Igneous rocks that have an intermediate composition and phaneritic texture are classified as diorite. These rocks are often characterized by their salt and pepper appearance due to the assemblage of both felsic and mafic mineral crystals that are visible with the naked eye. The intermediate composition is typical of continental crust that forms along convergent plate boundaries, and the coarse-grained texture tells us this rock cooled intrusively beneath the surface. Igneous rocks that have intermediate compositions but aphanitic textures are classified as andesite. These rocks can be difficult to distinguish from basalts in hand samples because they also tend to be dark in color and homogeneous in appearance due to the blended assemblage of the fine-grained felsic and mafic minerals. While some andesites may be lighter in color than some basalts, it is not enough of a distinction to provide certainty. A sample would need to be brought back to the lab for a more detailed analysis to determine whether it has an intermediate or mafic composition. So if the rock is intermediate in its composition and has a fine-grained texture, this is typical of continental crust that forms along convergent plate boundaries and is cooled extrusively at or near the surface. Obsidian is usually an extrusive igneous rock, easily identified by its glassy texture. It does form under certain intrusive conditions as well, but for our purposes, we're going to interpret obsidian as an extrusive igneous rock. It is typically black in color, although it can also appear in colors such as brown, red, or green. Because of its dark color, it is understandable to assume that obsidian is mafic in composition. However, it is more complicated than that, as the dark color is actually an optical property caused by minute mineral inclusions within the glass. This means that some obsidians may have just as likely originated from molten material that was felsic or intermediate in composition rather than mafic. In the field, the presence of obsidian along with other associated igneous rocks adjacent or nearby may provide some context from which the composition of the obsidian may be inferred. In other words, a lone sample of obsidian will not give us enough information to confidently assign a geologic setting to the rock. However, it is found along with basaltic or rhyolitic igneous rocks. We can interpret the likely geologic setting to be associated with divergent or convergent plate boundaries, respectively. For our purposes, in order to keep it simple and in line with the formation of obsidian from the sudden quenching of lava during an underwater eruption, we'll interpret obsidian as an extrusive igneous rock with a mafic composition associated with divergent plate boundaries, unless we have other evidence that would lead us to a different conclusion. Igneous rocks that have a vesicular texture are all extrusive, but we can classify them in a few different ways based on the type of vesicular texture and the color. If the rock is light in color, has an abundance of tiny vesicles with a frothy or meringue-like appearance, and is very lightweight such that it would float on water, we would classify the rock as pumice. Pumice, which cools rapidly, is going to be composed of fine volcanic glass and fine crystals of felsic to intermediate minerals, so we'll associate pumice with volcanism along convergent plate boundaries. If the rock is dark in color, has an abundance of tiny vesicles that resembles a sponge, and may or may not be lightweight enough to float on water, we may classify this rock as a scoria. Some scorias that cool quickly may also contain fine volcanic glass in addition to fine crystals of mafic minerals, so we'll associate scoria with volcanism along divergent plate boundaries. And finally, if the rock is dark in color, only has a few scattered vesicles, and is definitely not light enough to float on water, we would simply classify that rock as a vesicular basalt. These rocks will have the same mafic composition as basalt, so we'll also associate these rocks with volcanism along divergent plate boundaries. Finally, rocks that have a pyroclastic texture are all extrusive and can be divided into two basic classifications. Pyroclastic rocks that are composed primarily of fine volcanic ash with little to no class of volcanic debris, all smaller than a couple of millimeters, are classified as a volcanic tuff. If it is possible to interpret or determine the overall composition of the ash deposit, the name may be amended to reflect this by calling it a rhyolitic tuff, an andesitic tuff, or a basaltic tuff. If the pyroclastic rock contains large angular fragments that are a couple of millimeters in size and larger, the rock would be classified as a volcanic breccia. It's an Italian word, so feel free to pronounce it with your best Italian accent. But the word is derived from an old Germanic root word, breg, which means to break.